classes of these simples in terms of classes of some standard objects. Particular standard objects is those where we can compute dimensions of characters easily using some elementary combinatorics. And this requires getting hands a bit dirty in important elements. So the easiest case was when the p character is equal to 0, and then standards were the same as baby Vermas. And in the category where I don't fix the crescendo character, those are the following gadgets. So they were denoted by delta underlying with superscript 0 of mu. So those were induced modules, induced from the reduction of the barrel u0 of bf. And what I induce is, let me write f sub mu. So that's one-dimensional space living in degree mu. Okay. So and mu here is just a character of my torus. So mu lies in character lattice of T sub n. Now this is simple thing all of u chi. If you want to fix central character, and it mostly makes sense to fix the trivial central character 0, u chi 0 f mod t, we have what I will call delta underline w 0, and by definition it's delta underline 0 of the way w to minus 1 applied to minus 2 rho. Okay? And here w is in the affine Weil group. So w super a was the affine Weil group, which is w semi-direct with character lattice. Okay. Now that's very classical. Something which is I think new in our work. So the case when your G is semi-simple for simplicity, it's easy to reduce to this case, and chi is distinguished. So let me remind you that distinguished means that chi is not contained in a proper Levy. And the first observation here, which is also very classical, is that to this chi you can associate a certain parabolic subgroup. So we have parabolic, let's say PF1 inside of GF1, such that the Springer map from T star of GF1 mod PF1 to the orbit of chi is the resolution of singularities. And this has a bunch of implications. So first of all, we can choose chi such that it vanishes on P of 1 So the image of the zero fiber of this map just consists of such elements chi. And then chi is generic with this property. So what this means is that U0 of PF embeds into U chi F. Okay? And the target is a free module of the source of rank equal to P to dimension of G mod B. And then also from this, so since this map is birational, we know that the stabilizer of chi in P coincides with the stabilizer of chi in G. Maybe to make it a statement about group schemes, let me put one here. And in particular, we can assume that A, maximal reductive, subgroup of the stabilizer is in the levy LF of PF. So what we do next, we now fix mu in x of t, which is dominant for L. From this, we produce a dual while module. For purposes of this lecture, it's not that important what the module is. What's more important is that its character in the usual sense is the same as the character of irreducible in characteristic 0. And then we produce our standard object by inducing this up. So then we have standard W chi f of mu. So that's an induced module from U0 of P to U chi of this dual while module. And this naturally lives in the category U chi F mod, which is equivariant with respect to A, because A acts on every representation of L, and also it acts on this algebra here. So the induced module that we get naturally has A equivariant structure. Okay? So these are two cases which in some sense are opposite to each other, but in the general case is sort of extrapolates between these two cases. So let me tell you what happens for the general chi. So now we pick minimal levy. So let G0F be minimal levy. Containing chi, well, such that G0 0f1 star contains this element chi. Inside, I still have a parabolic and a levy as before, because now chi here is distinguished. Okay? So I can produce parabolic P as in the previous case. And I more or less repeat the same procedure. So what we do, let me write maybe delta underline chi of mu. So it's going to be an induced module from, so it will be induced to u chi f tensor over u0 pf maybe it's not a good notation, so let me write P0 for the subgroup in G0, and then it gives rise to a parabolic PF inside of GF. Okay? In a standard way, this guy will be the product of P0 and the barrel. Okay? So I induce from U0 PF of the same dual while module. So it's the same formula as before, but now the meaning is different. Okay? Yes?
So it's not clear whether or not the result will depend on the choice of the logic parabolic development. So even if you have a given logic developer, you have a choice.
I have a choice of a parabolic, and the result is going to depend on the choice. That's right. Okay? Levy is unique, and parabolic, well, sometimes unique, sometimes not.
When you say the result is going to depend on the choice of parabolic.
So the truth is that for these classes, for these objects, I'm only interested in K0 classes. And choice of parabolic, I think, doesn't really matter for that. Okay? So these are objects, and what is the natural home for this category, for these objects? What is the natural category where they lie? So this is going to be a category of certain equivalent modules, and what are these equivalent modules? So let me introduce some notation. So let me write that for the reductive part of the centralizer of the element chi now in the levy L. In the levy G0. Okay? So I take this minimal levy containing chi, and then I take the centralizer in that levy. So in particular, what this group is, so its connected component is a torus. So the connected component of this fellow is a torus. It's the connected component of the center of G0. And then we have this group is generally disconnected. And our module here is equivariant for that group, again, because it acts on everything, right? Bless you. So this fellow is Z equivariant. Oh, sorry, it's Z. That should be Z sub f, and I take the connected component of Z sub f.
What's going on now? Are you explaining how to reduce the general case to the case when I is distinguished?
No, I'm explaining what are standard objects for general chi.
But you do not assume that chi is the moment that chi is.
No, chi here is general. So the category that I'm going to consider is going to be the category of modules which are equivariant with respect to this group Z. Okay? So, this category is sort of should have the same equivariance as the category for the levy G0, the minimal levy which contains our important element. Okay? So, it's the same it's the same group as I would take in the distinguished case for the levy G0. Okay, so include the center, and otherwise it's this finite group that I defined before. Okay? So I take just the centralizer inside of that levy. It's very important. It's a group with pretty easy structure of my important element chi. And now let me tell you what are the standard objects which in the principal block. So in U chi 0 f mod z, so standards and let me denote them by delta underline chi sub w. So this is delta underline chi f of the weight w minus 1 applied to minus 2 rho, where w lies in what was denoted by w sub ap, and those are longest coset representatives for parabolic w sub p. Okay? So this is a labeling set for standard objects in the principal block. Questions? So, guys, if you are confused with all this notation, I have good news for you. So, I'm not going to consider this general case. So, what you need to know about this general case is that it sort of interpolates between the case of distinguished element and the case of chi equals 0. So, what you need to know is that there is such an interpolation. Now let's move on and let's talk about, this should be like maybe topic 2.2. So simples for distinguished chi. Sasha, 2.3, okay? So, what I want to explain, I want how to classify the simples, and I want to explain how to compute the characters. And to compute the characters, meaning classes in K0, I will need parabolic Kazhdan-Lusztig polynomials. So let me explain what those are. So I want to define the following element, T sub p of W, and W is going to be this longest coset representative. So by definition, this fellow is the sum over all x in W sub p in the finite parabolic minus v to power Lx times TWX. So this lives in the affine Hecke algebra. So the summands kind of, they correspond to all Weyl group elements in this coset, and I take them with certain factors here, right? And then a fact is that if W is in W AP, then the canonical basis element is expressed as a linear combination of these fellows. So it's a sum over U in W AP, some polynomial CP UW of V times this element here, TP of U. Okay? So this coefficient is known as a parabolic affine Kazhdan-Lusztig polynomial. It's a polynomial in V.
Is not defined, is it necessary for this fact?
Hmm?
I mean, is it fact for final group?
It's a fact for every Weyl group. Yeah. And so, what does it encode? So, these polynomials encode multiplicities in parabolic categories O. So, these fellows here correspond to parabolic Werner modules, and those are multiplicities of the simples, graded multiplicities. Okay? So now I can tell you kind of a main result for this class. So theorem, due to Bezrukavnikov and myself, it says the following. It says that irreducibles in the equivalent category U chi 0f mod A. So here A is a finite group. I'm in the case of semi-simple algebra and distinguished important element. I in one-to-one correspondence with left cell containing the longest element in W sub p, W0. So this is longest in W sub p. And also the shortest element in this set of maximal length representatives. Okay? So the symbols are parameterized by this left cell, and my notation is going to be if I take some element u in the left cell, I'm going to write L f u for the corresponding symbol. Yes. It is a finite set, and that's because my element is distinguished.
It's a left cell in the finite while group.
It's a left cell in a affine while group, which is finite because my element is distinguished.
But this is not all.
Well, it's because two-sided cells corresponding to distinguished orbits are finite. So this left cell is an affine while group. It's finite.
I mean, what did you just say? So that cells corresponding to distinguished elements are finite. So this is but it's not a cell.
It is.
It's not a cell corresponding to distinguished elements.
It lies in the two-sided cell corresponding to my distinguished element.
It lies in the two-sided cell.
Yes, and that two-sided cell is finite.
Is it actually clear it lies in that two-sided cell?
Hmm?
Is it clear that it lies in that two-sided cell?
Maybe not.
I mean, it's not proof that the W0P lies.
Yeah. So this is a classification of irreducibles. And now I can give you the character formula. So the class of LFU is the sum over LF maybe W is the sum over U in WAP CP UW of 1 times the class of the corresponding standard object. Okay? So that's a finite sum, because only finitely many of these numbers are going to be non-zero. So if instead of our category you consider parabolic affine category, and you put a class of parabolic Verma here, you will get a formula for the class of a simple in parabolic affine category. Okay? And of course you can ask, so what if I don't pick, let me write W here to maybe avoid confusion. What if I don't pick an element from this left cell and write my formula? So what if W doesn't lie in that left cell? The answer is I get 0. Okay? And of course, categorically, the statement means that my category is a quotient of the parabolic affine category in a suitable sense, where I mod out everything which belongs to smaller left cells. Questions?
So, you said last time that the main innovation here is introducing this equivalent.
Yeah.
So, what is the first one trivial example? In the case of GLM, A is trivial, right?
A is trivial and I have only one distinguished element. You can look at subregular.
So, what is the first one trivial?
The first one, well, okay, subregular in B2 is not going to work, but subregular in B3, I think.
G2.
Oh, subregular in G2, yeah. Okay, so I want to briefly comment on this equivalence assumption. So, of course, the initial goal is to understand the usual simple modules, not equivariant one. So I need to explain a connection between the usual simple and equivariant simples. Okay? So let's talk about equivariant versus non-equivariant simples. And the first thing to notice is that, of course, if I have some simple L in the equivariant category, it's completely reducible in the usual category. So I have a group whose representation theory in characteristic P is semi-simple, because P is very large. And if I impose the equivariance condition with respect to this group, then equivariantly simple module is just completely reducible. So the question is, what can we say about the decomposition into irreducibles in the usual category? And here is a theorem. So theorem number 2 of Raman and myself, which says the following. So assume that G is classical. Of course, for our question, it's only interesting to consider it outside type A, like BCD. Then we have the following two statements. So first of all, if you take the map from the equivariant K0 of the Springer fiber, for which I will use this notation, so it's equivariant K0, to the invariant part of the usual K0. So this is equivariant, and this is invariant. I just forget the equivariant structure on my sheaf. So if I do this, then this map is surjective. Okay? We can only prove it for classical G, and in order to prove it, we need to get our hands now very dirty in important elements. In principle, it's conceivable the same is true for exceptional types as well. But then once we know this statement, what we can prove is that every simple L is isomorphic to direct sum of pairwise non-isomorphic non-equivariant simples. So every simple which occurs in the decomposition of L occurs only once. Okay? So if we want to know, say, dimensions of this simple, we need to cook an equivariant simple out of them, and then divide by the number of simples which enter this decomposition. And this number is kind of computable if you know the representation theory of affine Hecke algebras, which is not so easy. Okay, questions?
Whether on these simple terms of the same dimension, or whether on these simple terms of the same dimension?
Yeah.
Sorry, so can you say really simple? Why one, why two again? So
It's not so simple. I mean, it follows from derived localization for representations. But it's in fact a consequence. So what? Okay. So for experts in the audience, this statement really tells you that there are no central extensions for the action of A on the set of isomorphism classes. Okay. And once you have no central extensions, you have a statement of this kind.
So is it true that if G is classical, then A is commutative, right?
Yeah, it's Z mod to Z several times.
So use factors. But in general, there is only one slot.
It can be like symmetric group on up to 5 letters.
But in the non-commutative case, somehow that's one.
No, I mean in the non-commutative case, indeed, there is no such implication, but then I assume that G is classical.
I see. So in the non-classical case, even if you knew one, you wouldn't be able to.
I wouldn't be, well, I mean, you're right. That's right.
You said that your real models are the same as the joint group model.
Yeah, let's say that here we have a joint group.
You do have central. For semi-simple group models, you do have central. See, for SP6, as you know much better than me. You do have central.
I think it's not this situation. No, I mean for distinguished elements, no. No. No, for 2 to 2, indeed you have some central extensions, that's true, but for distinguished elements it doesn't happen. Okay. All right. So this was a case of distinguished nilpotent. Now I want to explain the complementary case of the zero nilpotent element, which is pretty classical. So let's talk about simples in U00 F mod T. So there I have my Verma module, delta underline 0W, baby Verma, which surjects into the simple L sub W. So I want to know the coefficient of such module in such module. And so here, W is an element of the affine Weil group. And there is the following theorem, which is not due to us. I think it's kind of, it follows from results of Anderson, Janssen, and Sorgel for representations of algebraic groups, and some Kazhdan-Lusztig combinatorics, which was established by Lusztig. So the theorem says the following. So first of all, there is a stabilization result. So for fixed U and W, in W affine, and for all sufficiently large nu in the character lattice, which are sufficiently large, meaning that pairings with the simple roots are sufficiently large, the Kazhdan-Lusztig polynomial for the elements U times T sub nu, W sub T sub nu of V is independent of nu. Okay? So when you translate U and W deep inside the dominant chamber, the Kazhdan-Lusztig polynomial stabilizes. And then part 2 is that coefficient of the class of delta underline 0W in the class, I think I write U here, in the class of LW is the stable value of this Kazhdan-Lusztig polynomial evaluated at 1. Okay? So, here we still have the answer which is expressible via Kazhdan-Lusztig polynomials, but this answer is more complicated because we also need to do stabilization. In the previous case, there was no stabilization. Here, we really need to do it. And the reason is very simple, because this multiplicity here is translation invariant. If I translate both U and W by the same T sub nu, what happens to these modules is that I change the gradient simultaneously, right? And the multiplicity stays the same. So it cannot be really given by just usual Kazhdan-Lusztig polynomials because they don't establish this periodicity. So to achieve its periodicity, we need to proceed to this stable values. Okay? So let me give you an example. So in the previous case, unfortunately, there is no example which is computable. Here, there is a computable example of SL2. So, first of all, Kazhdan-Lusztig polynomials for phi in SL2 are very easy to compute. So, namely, if you have U and W in W are fine, then the Kazhdan-Lusztig polynomial CUW of V is minus V to power something like LW minus LU. For U less or equals than W in the Brio order. Okay, and otherwise it's 0. Okay, so all Kazhdan-Lusztig multiplicities will be equal 1 or minus 1. And also we can easily compute the multiplicities in the equivariant category. Remember, so I wrote for you an exact sequence for baby Verma module, which included 2 consecutive simple objects, right? Using this, you can easily, what?
And similarly, it's the plus 1, not negative.
What?
It's just the sum of 2 simples. So
No, it's a coefficient of delta in L, not of L in delta.
delta is the sum of 2 L.
And then you express this L's in terms of delta. You get an infinite sum. Okay? So let's, on the other hand, computing our category, let's compute the expression of L F0 of 1. Okay? So what is this? That's an infinite sum of delta underlying F of 1 minus delta underlying F of minus 1 plus delta underlying F of 1 minus P, and so on. So these are just consecutive labels in our equivariant category of modules. Okay? Which you get from these exact sequences. And it precisely, so I leave it as an exercise for you to understand this precisely fits into our theorem. Okay? So that's a special case of theorem 3. So I leave it as an exercise.
Just about notation. What is the one in brackets? Delta F.
That's the weight, highest weight of this module. So we learned last time that modules in our equivariant category are parameterized by weights. Okay? So that's the highest weight.
And for delta the same.
Yeah. Yeah.
1 minus 1.
Yeah. Well, yeah, sorry, it's shifted. So it should be 0. It should be minus 2.
0 minus 2.
Yeah, thank you.
Highest weight is 0.
Minus 2. That's right. And 2 minus p. My apologies. It was just shifted by row. Okay, questions? Yeah.
Just discuss an example or some.
No, I'm just going to tell you the result in the general case. Okay?
Sorry, Peter, the sum result operator, what sum result in theorem 1? Where you want to form a sum result about cases.
Yeah. Yeah. So we had two kind of results. The result in the distinguished case and the result for the nilpotent element. Now I'm going to tell you how the result in the general case looks like. And a warning, this is kind of, so this work is in preparation, but this general part is more in preparation than everything else. Okay? So let me call it, so here we talk about general chi.
Why, I'm still
What?
Just why 2 minus p is the last delta? Just minus.
Just minus p. Okay.
Minus here.
Okay.
Minus 2p.
That's right. If you use root lattice, yeah. Yeah.
Translate the roots.
So this you compute for the adjoint group. Okay, so so let me tell you, let me call it pre-theorem. And the statement of this pre-theorem is this, is that this case interpolates between chi distinguished and chi equals 0. In particular, the multiplicities that we want will be given by some stabilized values of parabolic affine Kazhdan-Lusztig polynomials. Okay? There is an actual statement here. I don't want to give it because it's quite technical. Okay? But there is a statement. Okay.
You have an exact sequence behind such formula.
Yes. And it's an exact sequence for baby Varma module.
Well, and what about the general case?
No, in general case it's much more complicated. All right. So this was statement of results. And now I want to move towards discussing how they are proved. But you need to consider some kind of stabilized category which should correspond to this quarter-infinite flag varieties. I mean, this statement is numerical. So maybe I should make a comment. The theorem that I am erasing now was proved using representations of algebraic groups, which are only available because we are dealing with zero nilpotent element. In general, there is no such tool. So we need to basically produce a different proof. And that's what we've done. Okay, so I'm going to ignore the case of chi equals 0 or the general chi case for now. I want to concentrate on the distinguished case. And I want to start with a tool which is kind of crucial in whatever you do with modular representation theory here. This tool is the derived localization theorem. Okay? So part 3 is some background for proofs. And we will start with localization theorem. So what this is going to allow us to do, so allow us to reduce our representation theory, the category to relate category of representations to category of coherent sheaves, essentially on Springer fibers. Okay? And so let me introduce this notation. Let me write curly B for G mod B. And then I have D sub B, which is a sheaf of differential operators. On B. And there is the following classical fact due to Billensong and Bernstein. First of all, the global sections of dB is U0. The central reduction of U of G at 0 central character. And there are no higher cohomology. And then the second thing that they prove later is that the functor gamma, which goes from the derived category of coherent dB modules to derived categories of U0 modules is an equivalence of categories. Okay? We will have equivalence of abelian categories in characteristic 0 for 0. Wait. So what I was going to say is that, of course, Billensong and Bernstein worked in characteristic 0, but the same statements are true in characteristic P large enough, like larger than Coxeter number. So this is also true for the field F with P bigger than Coxeter number by the work of Bezrukavnikov Mirkovich and Ruminin. So, and that's of course what we are going to use.
What notation? What's U0?
So that's Harishchandra's central reduction of U of G.
No percent.
No epicenter because this is originally in characteristic 0. And here, I mean, we don't impose epicentral character condition yet. Now, in characteristic P, there is a new feature which has to do with P center. And this feature is that over F, our sheaf dB is now an Azumaya algebra. And that's Azumaya algebra over T star of BF1. So let me just briefly remind you what it means to be an Azumaya algebra. So it means that you have a coherent sheaf of algebras where all the fibers, all the geometric fibers, are matrix algebra of locally constant rank. Okay? Particularly here, the rank will be P to twice the dimension of G mod B.
Whether or not the rank will be constant.
For connected variety, it will be constant. Okay? And that's the P-central phenomenon. So basically, kind of this sheaf here is a P-center of the sheaf of differential operators. Okay, so now in the left-hand side of this equivalence, we have category of modules over Azumaya algebra, which is sort of related to category of coherent sheaves. It's not equivalent because this particular Azumaya algebra is not split. So split Azumaya algebra is endomorphisms of a vector bundle. And this Azumaya algebra doesn't have such form. For example, because it doesn't have zero divisors. However, it splits on neighborhoods of Springer fibers. So let me consider now the Springer fiber. B sub chi 1, which lives in the cotangent bundle. And let me consider its neighborhood, which I will denote B chi 1 of H, which will be sort of a formal neighborhood, but it will be a bit larger. So that's a preimage of the formal neighborhood of chi in GF1. Okay? So this will be a known scheme, not a formal scheme. So maybe I should write formal less formally. Okay? And then we have the following result due to Bezrukavnikov, Mirkovich, and Romanin. That the restriction of our Azumaya algebra to this subscheme splits. Okay? So more precisely, there is a vector bundle let me call it V sub chi on this scheme such that the restriction of our Zumai algebra, so dBf restricted to this scheme B chi1 wedge is isomorphic to endomorphisms of V chi. And then once we have this result and we know the derived localization, we can have the following corollary. So corollary is that the functor R gamma of B chi tensor with a coherent sheaf is an equivalence of dB Koch on this neighborhood and modules over the similarly defined completion of U0F. Now let me make a couple of remarks about this. So these results here have a bunch of ramifications. For example, there is a version of this theorem where instead of honest central character, you work with generalized central character. Generalized Harish-Chandra central character. That's sort of important. Now for this theorem, you can also work with generalized P character. Here you will have coherent shifts which are schemes which are said theoretically supported on the Springer fiber. Okay? And you will have modules with generalized P character chi. Okay? So this category is sort of completion of. So here we deal with completions, you also have non-completed version. You can also deal with honest P characters. So here you can have the categories that we consider. Category of U chi 0F mod. And here you will have a category of coherent shifts on the Springer fiber, but there is a catch. You need to consider the Springer fiber as a derived scheme. And the scheme structure will be the structure of like derived intersection. Okay? So I'm going to ignore these difficulties from now on. Okay? So sometimes in this business you need to consider derived schemes, and I'm not going to mention it anymore. Okay?
So you need this because somehow you want to form something about one category being quotient with some other category.
Yes. Yeah. So the quotient category is a category of coherent shifts on the derived Springer fiber. So let's ignore this. And to finish this discussion in this part of class, I want to state corollary of corollary, which is kind of a nice numerical information. I already mentioned so corollary squared is that at least on the level of K0, all the subtleties do not matter. And what we get on the level of K0 is that K0 of the Springer fiber is isomorphic to K0 of the category U chi 0F mod. Okay? All right. This part is over.